This video teaches an overview of local linear approximation, which is a useful topic to tie together basic concepts covered in the limits unit and the derivatives unit. Local linear approximation is often used in the real world to be a way of estimating or quickly computing a specific value of a more complicated problem. Let's start with a simpler example. How would you estimate the fourth root of 17 without typing it into a calculator? Start by breaking down the equation into two separate parts. What is the parent function, and what is a known point that we can calculate that is close to the point we're zooming in on? The function we're looking at is what is the fourth root of x? The point we're zooming in on is when x is 17, but we know the value of the fourth root when x is 16, a number close to 17. The answer is 2 in that case. So we make our x sub 0 value equal to 16, something we can calculate. We need to find the tangent line of this equation at the x sub 0 value, which will be a good approximation of the tangent line at 17, the desired x value, without having to calculate that value. To find the tangent line of the function y equals the fourth root of x, use knowledge from earlier in the year in calculus. Start by taking the derivative of the function, in this case, start by converting the fourth root of x to x to the power of 1/4. Then we can easily use the power rule and get that f prime of x is equal to 1/4 times x to the power of 3/4. Find the slope, or mtan value, by plugging in the original x sub 0, into the equation. Here we get 1 over 32 as the slope of the line. Then we need a y value. To do this, we always plug back into the original function. Plugging in x sub 0, or 16, into the original function, we get 2 as the y value. Here in the Desmos graph, the point 16, 2 is highlighted on the red function, y equals the fourth root of x. The black tangent line to the point 16, 2 is shown. Notice how close to the black tangent line is to the red parent function at the x value of 17. It's a matter of less than 1/1000th. This makes it a good approximation. Let's put this into point slope form. Here's what we have. What can be replaced into the y on the left side of the equation? Well, going back to the Desmos graph, at the x value 16, the tangent line and the parent functions are equal. This means that to approximate the fourth root of 17, we can set the two equations almost equal to each other, or approximately equal. Because, as we saw before, although the tangent line is very close to the graph of the parent function at 17, they are not exactly equal. Now, plug in the x values as 17 and solve. We get 2.03125. If we put the fourth root of 17 into the calculator, you get 2.0305, which shows the power of local linear approximation. Now, let's quickly do another example with the same process. How can we approximate 4.092 squared? Start with the parent function. We're looking for some x value squared, or x squared. We can pick a close example that we know. 4 squared equals 16. So 4 is our x sub 0 value. So now let's find the tangent line of this equation when x equals 4. Start by taking the derivative using the power rule. The derivative of x squared is 2x. Plug in the x sub 0 value, in this case 4, into the derivative to get the mtan, or slope, value of the tangent line. Here the slope is 8. Finally, plug the x sub 0 value into the original equation to get the y value of the tangent line. Always use the original equation to find a y value. Then, put these given values into point slope form and isolate y. Here's what we have. We then know that at the x value of 4, in both the tangent line and the parent function, the y value is 16, because this is where they intersect, or they're equal at the exact point. So at the x value of 4.092, we can see that the parent function x squared would be approximately equal to the tangent line when x equals 4. Then we can plug in x in for 4.092 on both the left and right sides. We see that 4.092 squared is approximately equal to 16.736. If we put 4.092 squared into a calculator, we get 16.74464. So this was a very successful approximation. Let's quickly look at this conceptually on Desmos. We have the x sub 0 value and its corresponding y value plotted, and then the tangent line of this point that you can barely see because of how it perfectly hits this curve. Then when we go to the 4.092, the desired value, we see how close the tangent line is, but it's not exactly there, which is why it makes such a good approximation.
Local linear approximation, LLA, can be used to estimate population at years or times that are unknown as long as there is an approximate known value. In finance, LLA can be used to determine the complicated behavior of stocks to look at when to take risks. And in physics and chemistry, LLA is used to look at when cooling graphs or curves might reach equilibrium.